Hello, how's it going? Hope you guys are doing great today. We are going to jump into a new topic in astronomy, and it's really talking about the differences between stars. And I want to show you a picture to start with. So here's a picture of, it's got a fancy name. It's called a globular cluster. Basically, it's a bunch of stars all grouped together in the same place. They're all together. And I wanted to share this verse that I read recently. Um, Paul is talking about the resurrection, so Easter, talking about how we will now that Christ has resurrected, we have the promise to be resurrected in the end, and we will have new bodies, and our bodies will be raised in glory. And he was comparing the glory that we will have to the glory that the stars have. So I wanted to read this verse. It says, "The sun has one kind of glory, while the moon and stars each have another kind, and even the stars differ from each other in their glory." What a cool verse, just to set our minds on our Creator, knowing that He has created each star unique. All these stars that we talk about, there's so many of them, and each one is created unique and different, and each one differs in their glory from another. They all are unique in their own way, just like each human being is different. It's just amazing to think about. So the question that I want to start us with today is we kind of ended here last time where we were talking about how stars form, how God creates new stars. He takes a nebula, he takes the interstellar medium, which is the matter that's in between the stars. Whatever is out there between the stars, he takes the dense parts and uses gravity to condense them and get them smaller and smaller. So when that happens, they get smaller and smaller, which means they drop in their luminosity, and they also get warmer. And so they kind of drop down onto the main sequence. And then they begin somewhere on this red line. That's where stars begin their lives whenever they begin fusing hydrogen into helium. And that's what we call hydrostatic equilibrium, when they're balanced. They land somewhere on that line. We call that line the zero age main sequence. It's where stars begin their adult lives. It's where they begin fusing hydrogen into helium, and that is where they spend almost all of their life, just virtually everything. But there is some other things that happen, which we'll get into. But the question today that we're going to focus on is this: why are some new stars hot and bright like this one? It's over here. The hot temperatures, O, B, A, those are the hotter ones, right? Why are some stars hotter and brighter, but then other stars cooler and dimmer at the beginning of their life? I mean, what makes the difference? Are they all made out of the same stuff? Don't they all have the same composition? They're all forming from this, you know, nebula, this cloud in space. So shouldn't they all be the same? Well, they're not. There are a lot of different stars, different types of stars, and they fall somewhere else along this main sequence, a zero age main sequence. They have all these different possibilities. So why the differences? So to answer that, we have to remember that scientists use models to try to explain what they see among the stars. We create models of stars on a computer a lot of times, factoring in like how much we know about gravity, how gravity works, what we know about thermal pressure. Whenever you push stuff together in a lab, you know it gives off certain amounts of forces. So we can simulate um, pretty well what happens inside of a star. And we have a star nearby, the sun, to test out our models on. And that's what astronomers spend a lot of time doing, is they look at the sun and test out their models based on what they see in the sun and what we get from the sun. So models help explain how stars behave, and they also help predict how stars will end their lives too. So we're talking all about models. That's what we're using. The theory of stellar evolution, how stars change over time, it's all one big model. It's a model of how stars form, how they live, and how they die. And that's what we're talking about. So scientists are using models, and we're using models today to kind of talk about how stars form. This is a model, a computer model of how a star begins. You can see this is like a big gas cloud, and it's all kind of swirling in. Gravity's kind of pulling it in, pulling it together. And excuse me, you'll notice right here in the middle is where the protostar is. That's where the star is beginning. And then this leftover kind of like these other chunks out here, this is part of the nebular hypothesis of how planets form. So the way astronomers kind of view the model of the natural world, how the forces predict certain things about planets. This is the theory that when stars form, there begins to be this spinning disk around the stars, and that's where the planets form from as well. And so this is not some kind of excuse to get God out of the equation of creating planets. This is simply just trying to explain how it happens. And we as Christians would be confident to say, well, this is how God does it. And so this is the theory of how planets form. They form alongside with stars, but we're not going to focus on that today. We're going to focus on what makes one star different from another. And I just want to point out real quick also, the process that you're looking at, the process you're watching, if you look at the top here, you'll see a timeline, like a time prediction, and it's in years. And I just wanted to point this out because we don't say this a lot, but the things that we talk about in here about how stars change and how they form, it takes lots and lots and lots of time. Things in space are so big, and gravity is just so weak that it appears to take unimaginable amounts of time for many things to happen, like millions of years. And and that shouldn't scare you when I say millions of years. I'll tell you the truth. It used to scare me when I was in high school, and I would just kind of like scoff at it, like, millions of years. But again, we're not discrediting God at all. We're just trying to explain what we see with our senses, and based on what we see, things in space are just so big and gravity is so weak that it takes so much time for anything to really happen. And it's estimated that this process of star formation takes about 10 million years on average. Now, nobody's been watching it for that long, right? Of course, but again, we're using models. We can't see everything in space. We can't be around long enough to see everything, but we can get a good glimpse of a lot of different things and kind of piece together a story. And that's what we're trying to do. So things like this take millions of years based on our models. And also based on our models, coming back to the central question today, how is one star different from another? The latest models suggest that there's just one main thing that makes a star different from its partner star. And the one main thing that makes stars different from each other is their starting mass. How much mass do they start with at the beginning of their life? That single factor determines everything else about a star's future. It's amazing. It's so simple. That's the amazing part. It's just so simple. What the mass is when a star begins its life will determine everything else that happens to it. Right? Because stars don't make choices. And so there's not a lot that can happen in a star's life other than how much gravity is pulling it in. So let's look at this question together. Which star do you think will be hotter, a high mass star or a low mass star? Okay, simple logical deduction following. You ready? Okay, follow me here. Which star has a stronger gravity? Low mass or high mass? That's got to be obvious, right? That's the high mass star has a stronger gravity. Well, if you remember, if the high mass star has stronger gravity pushing inward, pushing down, we're going to act like down, it means pushing in, right? So it's pushing down. Gravity is stronger for a high mass star than it is for a low mass star. Well, remember, stars have this balance between gravity and pressure from fusion. So gravity pulls the star's weight inward, but then something has to balance that gravity coming back out. And that's nuclear fusion, or the pressure that comes from nuclear fusion. And so pressure must be balancing the gravity. That means that the high mass star is going to have more pressure too. So high mass has more gravity. It also means it has more pressure. So in order for the high mass star to balance its strong gravity, it needs a lot of pressure from fusion. Okay. That also implies that the high mass star must be hotter, right? Because in order for it to have more pressure, more fusion, that means there needs to be more nuclear reactions happening. More fusion reactions need to happen, which also means more energy is getting released. and it's hotter. So they go hand in hand. The higher mass stars have more gravity pushing in, which means it can have more energy being exerted, and more temperature there. So high mass stars are hotter. So if we do a little comparison here, and I'll have you do something like this, but comparing the high mass star and the low mass star, we already said the high mass star has higher gravity. In terms of pressure, has to be the high mass star again, because pressure is what balances gravity. Because it's got more pressure in the core, that means there must be a hotter core. It must be hotter. So high mass star is hotter, low mass star is cooler. And then finally, the luminosity of the star is how much energy it gives off. It's directly related to the temperature and pressure in the core. So the hotter it is in the core, the more energy it's going to be producing, because the more fusion reactions are going to be happening. So it's higher on every measure between the high mass and the low mass star. So we already said this. Which kind of star would produce energy faster? The high mass star. So the way that stars are different is simply that they have different masses. Mass determines everything about the structure of a star, how it's built, and where it falls on the main sequence. More mass means more strong gravity. That means a higher temperature, higher pressure, more nuclear reactions, more energy, more luminosity. Okay, so there's an important distinction here that comes up now. Since it's just the mass that determines everything about the star, and the higher mass stars are going to be having more nuclear fusion reactions, more and more nuclear fusion reactions. That means that high mass stars are going to burn through their fuel of hydrogen really quickly. Remember, stars fuse hydrogen atoms, two hydrogen atoms fuse together to make helium. That's what stars are producing. And really, I guess it's four hydrogen atoms come together to make one helium atom. And so stars are burning. We say burning through hydrogen, but really they're just taking hydrogen and turning it into helium. So the high mass stars do that quickly because they have to. They have to keep going in order to keep balancing the crushing weight of the high mass star. Low mass stars can burn through their hydrogen really efficiently. They don't need to use as much of it to keep going, and so they're more fuel efficient. So I like to compare them by saying that lower mass stars have much longer lives than high mass stars. High mass stars kind of live fast, they die young. They're like rock stars. They gotta do it all and they gotta live it all. And they die quick. I mean, they die young. And I compare it to a semi truck versus a smart car. So this is just a great comparison because if you wanted to compare the fuel efficiency, the high mass stars are going to be a lot less fuel efficient. They're going to die quicker. They're going to run out of fuel a lot quicker than the low mass stars. Even though high mass stars do have a bigger fuel tank, you can put more gallons in a high mass star than you can a low mass star, but that doesn't even matter. High mass stars burn through it more quickly. It's just crazy. High mass stars burn out much quicker than low mass stars. Here's a table that kind of gives you the best models that we have today that have been tested and refined, and this is the best model that we have today to predict how long different stars will last. This is their lifespan. So our sun is right here. One times the solar mass. That's our sun. Our sun is estimated to have about 10 billion years of fuel available for it to burn. 10 billion years. I mean, that's just unfathomable how long that is. Um, and so right now, the scientific model suggests that our sun is about halfway through its life. So it's been burning for about 5 billion years. And there's various different kinds of evidence that point to that. We can talk about that later. But then the other stars, the more massive stars, have shorter lifespans. So as you get up here, 10 times the mass of our sun, it just gives you a life of 32 million years. That is so much less. That's like less than 1% of the time that our sun will live if you go up 10 masses, like 10 times the mass of our sun, is less than 1% as long of a life. So much, much less of a life. And then you go up to 30 and 60, a 60 mass star, those are very rare. But if a star is so massive that it's 60 times the mass of our sun, it only lives for a short 3 million years, short on the scale of space. But then if you go down here, if you go to smaller stars, stars that are less massive than our sun, they are extremely fuel efficient. It's like you don't even have to worry. They're just always going to be there in terms of a human perspective. They are estimated to be able to burn through their fuel in trillions of years. They have 1,000 billion is a trillion. So they are estimated to last for as long as the universe has been in existence, basically, is what scientists would say. The model, the Big Bang Theory, predicts that our universe is about 13 billion years old, 14 billion years old. So if there have been any stars that have formed that are less massive than our sun, it's likely that they've been here since the beginning. And we can test that model by looking at what those stars are made of, and we can also kind of see how they're burning. And we'll talk about that later as well. So back to the original question, and then we'll finish up here. Why are some new stars hot and bright while others are cool and dim? And the answer to that is a one-word answer: mass. The mass determines everything. So the more massive stars are going to be the ones that are at the top edge here, and the less massive ones are going to be down here. I have some other pictures that show that. So here's a, a diagram of what happens when new stars form. They start up at the top right up here, where they're a nebula, and then the nebula condenses and gets smaller and smaller and hotter, and so they kind of drift over here to the left and down for the most part. But the higher mass stars just kind of shoot over here, and so you're left with a main sequence of the highest mass stars are at this end, and the lower mass stars are at the other end. And here's another example of that. So it's kind of a pixely image there, but it's okay. So yeah, that's what determines the differences between the stars. And on our next lesson, we're going to kind of fast forward a little bit and see what's going to happen when these stars do run out of fuel. And that's where it gets real fun. So I'm excited about that. Let me know if you have any questions on the board. And I hope you guys have a great day.